Welcome back. In this video, we're going to talk about the whole numbers under division. So our fourth operation in this section. And again, this is another example of a binary operation where I take two inputs and I get one output. So there are two main views that that your textbook presents when thinking about division. So there is this idea of sharing division, and here there are a specified number of groups, and we are asking how many objects end up in each group once they're distributed. So here there are a specified number of groups, and we are asking how many objects are in each group. And let's see here. So here's an example of this sharing division. So the sharing division, I have 20 kids, and they're divided into 4 teams with the same number of children on each team. And I want to ask how many kids then are on each team. So here I'm starting thinking about the teams, and one kid is going to walk to each group. Okay, so one kid walks to each group. Okay, and so I do this until I end with my last child, my 20th child. And I see how many children are in each group, and I see that there are 5 kids in each group. Okay, so this is the viewpoint of, or perspective of sharing division. There also is the view of measurement division. And so this is the opposite view. Here we have a certain number of objects you are measuring out and to be placed in each group, and asking how many groups are there. A certain number of objects you are measuring out, measuring to each group, and ask how many groups are there. Okay, great. So in this case, I am going to take, so if in this same analogy, if I have a class of 20 kids and I wanted to divide into teams of 4 kids, I just break off, the first 4 kids and the second 4 kids and the third 4 kids, and so on. Oh my goodness. And when I do that, I see that I have 5 groups. So it's really the same division problem, but really asked in 2 different ways. Okay, so a couple more examples, helping us understand the difference between this measurement and sharing division. So first, so we want to class each of the following division problems into examples of sharing or measurement division. So example A, here we have a certain airplane climbs at a rate of 300 feet per second. At this rate, how long will it take for the plane to reach a cruising altitude of 2,700 feet. So we want to think of what we're doing is we're going to measure the first 300 feet, then the second 300 feet, and the third 300 feet. And we'll see we have to do this 9 different times. And so this is an example of the measurement division. Because we're kind of like measuring them out bit by bit. In part B here, we have a different example. We have a group of 15 friends pooled equal amounts of money to buy lottery tickets for a $1,987,005 jackpot. If they win, how much should each friend receive? So what this is, way we can think of this is you might think of taking $1 and giving it to each friend 15 times and then starting over and doing this until you run out of money and then seeing what each friend has. So in this case, this is an example of sharing division as opposed to that measurement division. I'm not going to measure this out because I wouldn't know how much to measure for each friend in the first place before doing the division. Okay, an example C here, we have Shauna baked 54 cookies to give to her friends. She wants to give each friend a plate with 6 cookies on it. How many friends can she give cookies to? So here, Shauna starts with these, starts with the cookies, and she's going to put 6 cookies on one plate and then 6 cookies on the next plate. And she's going to do this until she runs out of cookies. So here, this is an example of that measurement approach or measurement view for division. So there are also 2 main different approaches that we can use for division in teaching it. So there is one approach, which is called similar to the missing addend approach that we had for subtraction. We have a missing factor approach for division. Now, in the missing addend approach, what we did was we said, hey, subtraction is related to addition. And so we will define this, we can think of defining the subtraction in terms of addition. Well, it's the same thing. Division is related to multiplication, so we are going to define this division in terms of multiplication. So here we start off with 2 whole numbers. Let's assume that one of them isn't 0, so we're not dividing by 0. We'll talk about why that's a problem later. So when I divide A by B, I get another number C if and only if B times C is equal to A for some C in W. So again, similar approach to that missing addend approach that we had before. Okay, great. And in this case, this piece, whenever we're talking about addition here, this piece is called our dividend. This piece is called our divisor. And C is called our quotient, or in this case, our missing factor. Okay. Great. So, yeah, okay. So the last approach that we're going to talk about with regards to addition is when we talked about multiplication, we had the approach of repeated addition. Well, in the operation of division, we also have a repeated subtraction approach. So for example, if I want to divide 12 by 3, I can use this measurement model really nicely. And so it's 12, 9, Okay, so if I'm dividing 12 by 3, I would start by I might start at 12 and I'd repeatedly subtract 3 units till I got to the smallest number here, and I would see that I subtracted 3 4 times. And so 12 divided by 3 is 4. I can also think of this, so like not using the measurement model, but just using subtraction. If I start off by subtracting 3, I get 9. I can subtract 3 again. I get 6. And I can subtract 3 one more time. I get 3. And the last time I end up with 0. Oops. Here. And here again, I can see the number of times that I subtracted 3. 1, 2, 3, 4 was 4 different times. And so 12 divided by 3 is that. Okay, so of course, just like our other operations, division has a few properties that are worth noting. So the first one, we have asked if each of our if our set of whole numbers is closed under each of our operations, and in this case, the whole numbers are not closed under division. And we can see that because if I take any 2 whole numbers and I do division, I may not necessarily get a whole number out. So now if I take 6 and I divide by 3, I get 2, which is a whole number. But if I take, let's say 6 and I divide by 5, that's not a whole number. And I'll actually write it. Which is not a whole number. That's 1 1/5 or 6/5 is fine too. Okay, and of course that's true for lots of different pairs that we can choose. This division is also not commutative because it matters which order I do the division, right? So let's say 4 divided by 2 is equal to 2, but 2 divided by 4 is equal to 1/2, right? And these are not the same. Great. So 2 properties that division does have. Well, the first one is, so as long as we are not dividing by 0, so as long as a is not 0, but if any other whole number, and I take 0 and I divide by a, I get 0. So when I've looked at justification for most of these properties before, I've really been looking at some sort of maybe example or some visual representation of an example. For justification in these two, I want to look more at something maybe a little bit more, I guess what we would call it rigorous. And so an example of direct reasoning. So here, in order to see why this is true, I think it is really helpful to think about and to use this missing factor approach to division. So what I'm going to do is I'm going to take my division problem and I'm going to turn it into a multiplication problem. Okay. So I'm going to assume a is not equal to 0 because that is my blanket first assumption. This only works if a is not 0. Well, if 0 divided by a is some constant, we'll say we don't know that it's 0 yet, but we're asking about this. We're asking about 0 divided by a. Then that means a times c should equal 0, right? That's exactly what my missing factor approach says. It says, if I move this over here, A times C should equal this. Okay, well, we know something about multiplication. We know that if A times C are equal to 0, specifically, we know one of them has to be 0. And this is from my zero divisor property of multiplication. So if A times B is 0, then one of the two things had to be 0 to start with. Well, we assumed that A wasn't 0, so that means that C has to be 0. And that's exactly what we were trying to show, is that 0 divided by A has to equal 0. And that's exactly what we've got. Okay, so this is an example, like I said, of direct reasoning, which is one of our examples of what did they call it? An example of an approach to problem solving in chapter 1 that we mentioned. There's an example of that. So maybe it would be, so I guess this next property that we're going to talk about with division is called, so it is that division by 0 is always undefined. So maybe now would be a good time to maybe pause this video and see if you can use a similar argument to the one that we used in property 1 here to show that if I take any number, A, and I divide by 0, so i.e. A divided by 0 is undefined, then this is undefined. So I encourage you to pause the video here and play around with this direct reasoning approach. And when you're ready, I'll come back and I'll finish off my explanation here. Okay, so I probably should have given you a hint, which is that I think it's helpful in this case to divide this into 2 different cases. So let's first, we made no assumptions about A at all. We're just kind of assuming that it's a whole number. But let's assume that A is not 0. So suppose A is not 0. And we want to assume A divided by 0 is equal to some number, some whole number. Okay, so what I want to show is that like this can't be true because I want to show that this is undefined. So let's go ahead and use our missing factor approach again. And so this means that 0 times C is equal to A, but 0 times C should be 0 by that 0 multiplication property, or multiplication property of 0, I think we called it. So this means A is equal to 0, right? 0 times C is A, and it's also 0, so A has to equal 0. And if A is 0, well, that's a problem because I assumed it wasn't 0. This is what we call a contradiction. If I suppose one thing is true and I show that it's in fact false, I get a contradiction. And so this also has to be false. Okay, so it's like, let's say, there's lots of real world examples of this, and my son is creeping up on me in the corner, so this is very hard for me to come up. He's carrying a toy Santa Claus and a Christmas tree, so it's quite distracting. So let me think here. There's lots of real world examples. So yeah, if I assume it's, so I might say something like, suppose Sally comes home with, so if Sally comes home with an umbrella, that means it was raining. And if Sally comes home and she's, oh wait, this is not gonna work as an example. I apologize, now my dog's barking. I'll come up with an example in a moment here. Let me pause. Okay, so here's a real world-ish example of using a contradiction. So say you're trying to figure out how to get to the airport in time for your flight. You say, okay, my flight is at 2, I want to get there 2 hours early, and I want to see if I can take the bus to the airport. And you realize, and you're like, okay, well, let's assume I take the bus to the airport. Well, the earliest bus leaves at 11 a.m. and it takes me, it takes an hour and a half to get to the airport. That puts me there at 12:30, but that's not 2 hours before my flight, so I won't do that. So that's kind of an example of using a contradiction. You got to something that you didn't like at the end. So, I mean, you got to something in the contradiction, you get to something that's false, but that's kind of a real world instance of this contradiction. You start off by assuming something and show that it has to be false. Okay, so that's our first case. In our second case, well, we started off by assuming A was not 0, so we have to worry about the other case where A is 0, right? So suppose A is equal to 0, and we are going to think about what happens with 0 divided by 0, and suppose that that equals some whole number. So let's say in this case, it equals a whole number. So then 0 is, by that missing factor property, 0 is equal to 0 times c, right? That missing factor property says that I can, this is the same as tossing this 0 over to the other side. But this is true for every single whole number c. And so that would mean that 0 divided by 0 equals 1, it equals 2, it equals 3, it equals 4, it equals a million, right? And that's bad too, right? So this means it's indeterminate. Okay, so in our first case, we got, there was no possibility. In the second case, everything was a possibility. In which case they're both undefined. Great. So this is an example of indirect reasoning. This reaching a contradiction type of thing. Like our bus example is an example of indirect reasoning. Great. Okay, so those are 2 properties that we're going to talk about with division. There's one other little term that we want to talk about in this section, and it's the division algorithm. And written out this way, it seems somewhat complicated, but it's actually something you have seen before and maybe just haven't given a name to. So how the division algorithm works is if we take any 2 whole numbers, any of them, and as long as we assume one of them is not 0, then, sorry, this means there exists, or there are. So there are 2 other whole numbers, so that we can write A is equal to B times Q plus R, and this R number is between 0 and B. And what this what we can really, maybe this will be helpful to call these things by their name. Here, we can think of, so B is the divisor. So B is what I am dividing A by. Q is the quotient. And R is the remainder. So what this really is saying is it's giving, it's using that like missing factor approach characterization to talk about the fact that if you have any two whole numbers, you can divide one into the other and you'll at most, or at worst, I guess, get a remainder. And so how this division algorithm works in practice is, in practice, I guess, is we can imagine that if I'm dividing 57 by 9, well, what I would do is I would first look at some multiples of 9. So 9 times 4 is 36, 9 times 5 is 45, and 9 times 6 is 54. Which isn't quite 57, but it's not, if I did another multiple of 9, it'd be too big, right? So if I add now 3 to both sides, oops, 9 times 6 plus 3, that should give me 57. And that's exactly what this division algorithm is spelling out here. So here, 57 is like my A, 9 is like my B, my quotient then is 6, and my remainder is 3. And the thing to notice here is that this remainder, 3, is less than B, my divisor. It's less than 9. So I could have chosen other numbers besides 6, like I could have chosen 5 here, but then if this were 5, I'd have another, let's see, I'd have another 9 to add here, so this would be 12. And that would be too big. So this is like a unique way to write this in subset. And so what this tells me is that this is 6 with a remainder of 3. And so of course I can do this as like my longhand division. I can think of this is, I guess using this other notation is really doing the same thing, but dividing 57 by 9. I ask myself, how many times does 9 go up to 57? Well, it's 6 times. 6 times 9 is 54. And when I subtract, I have this remainder of 3 left over. And that's all the division algorithms. And last but not least, I can also think of this in terms of that measurement model. And so if I wanted to, I could, in terms of this measurement model, if I'm looking at, we said 57, well, if I want to divide it by 9, I would move back 9 units. And I'd notice I had to do this 6 times before I almost got to 0. So this is 6 times, I think. And I would still have a remainder of 3. So that's just using that measurement model. Okay, so a couple other examples just to make sure this is solidifying. If I take 44 divided by 13, I want to ask myself how many times 13 goes into 44. So I am going to, let's see, I noticed that maybe 13 times 3 is equal to 39. And if I add 5 to both sides, I get 44 on the right. So this is 13 times 3 plus 5 is equal to 40 in terms of my division algorithm. or what this really means in terms of like remainders is that 44 divided by 13 is 3 with a remainder of 5. And this remainder of 5 is, of course, less than 13. That's this important piece. Okay, one last example. If I want to divide 96 by 8, I notice that 8 times 12 actually is 96 in this case. So I don't need to add anything. My remainder is just 0. So if 8 turns out to be a divisor of 96 here, then I just have that R piece is 0, and that's totally fine. So it is okay for my remainder to be equal to 0. Oh my gosh, equal to 0. Okay, so a couple more examples just to clarify any odds and ends from this section. So again, we have another question about whether the following sets are closed now under multiplication and not under addition. So remember, closure has to do with both the sets and the operation on that set. So I would first, so looking at A here, if I take 2 times 2, that's 4, that's in this set, so that's good. But if I say take 2 times 4, that is 8, and that is not in the set. So A is not closed since 2 times 4 is not in the set A. For part B, 0 times 2 is contained in here, it's just 0. 2 times 4 should be in here because that's just 8. These are just multiples of 2. So I would expect this thing, I mean, you might want to try a few more to make sure this is solidifying for you, but since this is all multiples of 2 and we're just multiplying multiples of 2 together, so this is multiple of 2 times a multiple of 2 equals another multiple of 2. For this example here, again, 0 times 0 is in here, 3 times 0 is in here, but 3 times 3 is not. So this is an example of one that is not closed because 3 times 3 is equal to 9, which is not in this set. However, even though D looks really similar, there's an important distinction, which is that 1 times 1 is still 1. So this set is in fact closed because 0 times 1 is 0, and that's in there. 0 times 0 is 0, and that's in there. So in fact, this thing is closed since 1 times 1 is equal to itself, which is in this set. Likewise, E is closed and F is closed. So both of these are closed. So notice that the set E is closed under multiplication because 1 times 1 is itself. And same with F because 0 times 0 is itself. But this set would not be closed under addition because 1 plus 1 is 2, and that's not in there. So again, just reiterating that both the set and the operation matter here. Okay, so here we're talking about multiplication, and I think the difference here, I think these are just adding 2. So this should give me, I believe, every odd number bigger than 5, unless I'm mistaken, or equal to 5. And let's see, notice if I multiply any 2 odd numbers, I get another odd number, and they're only going to get bigger. So this is another example of a closed set. It's an odd number times an odd number is equal to an odd number. I think that this one should also be closed. Those are multiples of 7. And I think I will be closed as well. Those are powers of 2. And since we're multiplying, that should be fine. Yep. Or powers of 2, not multiples of 2. They're powers of 2. And odd whole numbers, just for the same reason, I think that should be closed as well, because an odd number times an odd number is another odd number. Great. Okay. In this example on page 112, we want to identify the whole number property being illustrated. So this first example, we have 4 times 5 is equal to 5 times 4. This is that multiplication is commutative. Oops. For this next one, this one's a little tricky. So now don't be thrown because there are parentheses involved here. But what's really important about this operation is, or really the distinction between the left side and the right side is only that 6 and this thing have switched orders, right? So this is actually another example of commutativity. Of multiplication. What's different in C, though, is that, so the left-hand side looks similar, right? Different numbers, but similar form. But here, the right-hand side, this 5 is now distributed to each of these new terms as opposed to being like the switched order. And so this is an example of the distributive property. Of multiplication. And now D looks again very similar. I have a similar left side here with some whole number times x plus y. But on the right, what we're really using is the fact that this whole number is 1. And so this is the identity property. Since what happened was I got the same thing, that x plus y as was multiplied by 1 in my solution. Okay, in the next video, we'll finish off chapter 3. We'll be discussing ordering and exponents. So I will leave you here shortly, and I'll see you next time.